Mabuhay, fellow physics teachers! Welcome once again to your program, Physics in Everyday Life. In the previous episode, we developed a kinetic molecular model for matter. We used the model to interpret the pressure and temperature of a gas on the macroscopic scale in terms of molecular motion. We tested the model against experimental data and found it to be consistent. In today's episode, we shall deal with thermodynamics, the study of heat and its transformation to mechanical energy. We will go back to the macroscopic level and study mechanical work, pressure, and temperature of gases and their roles in energy transformation. Today we will focus on the applications of the facts and ideas of science to the solution of everyday problems. Such use of knowledge for practical benefit is known to us as technology. So keep us company and we will deal with the basic theory of heat engines. Before we begin our study of engines, let us first distinguish between temperature, heat, and internal energy. In the previous episode, we learned that on the microscopic scale, temperature is a measure of the average kinetic energy of the molecules, as shown by this model here. And that it is measured with a thermometer. In everyday life, we know that when heat is added to a system, say water in a container, its temperature rises, as shown in this setup. This close relationship between temperature and heat has led to the false conception equating heat and temperature. We also know from experience that when two systems at two different temperatures, say this hot coffee here and this cold milk here, when these two are mixed, like this, then the mixture attains a common temperature, as shown here. The faster moving molecules of the hot coffee transfers some of their energy to the slower moving milk molecules. Consequently, the temperature of coffee falls and the temperature of milk rises. The transfer of energy stops when thermal equilibrium is reached and the mixture attains a common temperature. The energy that transferred from the hot coffee to the cold milk is what we refer to as heat. It is a form of energy which transfers from one system to another because of differences in temperature. But not all heat transfer to a system is manifested in a change in temperature. For instance, even if we continue applying heat to boiling water, its temperature does not rise. What happens to the heat absorbed by the water molecules? All right? Let's show this setup here. We have boiling water and look at the temperature reading. Okay, so let's take a closer look at our setup. we can see steam rising from the water surface. Making the flame bigger here does not cause any temperature increase, but increases the rate of turning water into steam. The absorbed heat causes water to change phase from the liquid phase to the gaseous or the vapor phase. The process of changing from the liquid to the gaseous phase is called evaporation. The reverse process, the change from gas to liquid, is called condensation. In condensation, heat is released by the system to its surroundings. In the same manner, when ice becomes water in the process called melting, as shown here, it absorbs energy from the surroundings. The temperature of the ice-water mixture remains constant until all ice have melted. And the same is true when water turns to a solid in a process called freezing, but energy is released. In general, when heat is added to a solid or a liquid, the solid or liquid eventually change phase. A solid will melt or liquefy, and a liquid will vaporize. Conversely, heat is extracted when a gas condenses into a liquid or when a liquid solidifies or freezes. Energy is absorbed for both melting and evaporation. And conversely, energy must be released during condensation and freezing. Of the three phases of matter, we can see that the molecules of solids are closest to one another, and those of gases are the farthest. Recall that potential energy is greater when the distance between interacting bodies is longer. Hence, we can say that the potential energy of the molecules of a gas is greatest compared to those of liquids and solids. So when heat is transferred to a system, it can cause a change in temperature as well as a change in phase. In terms of energy, the heat absorbed is transformed into kinetic and potential energy of the molecules of the system. The sum total of the kinetic and potential energy of the molecules is called internal or thermal energy. Let us now summarize the differences between temperature, heat, and internal energy. Temperature is the measure of the average kinetic energy of the molecules of a system. Heat is a form of energy which transfers from one system to another because of temperature difference. Heat transferred can be manifested as a change in temperature or a change in phase. Once heat has transferred to a system, it ceases to be heat. It is transformed into the internal energy of the system. Internal or thermal energy is the sum total of the kinetic and potential energy of the molecules of the system. Earlier we mentioned that when water boils, its temperature no longer rises even if the flame is increased bigger. Instead, the water turns into steam more rapidly. Applied to daily living, we will do well to heed this advice. When cooking, lower the flame once water starts to boil to conserve on fuel and prevent scorching. A large flame will not reduce cooking time. More tips when we return after this short break. Don't go away. Welcome back, fellow physics teachers. We shall now apply the ideas and principles related to heat and thermal energy to engines. Engines change the internal energy of a gas into useful mechanical energy. For example, a steam engine uses the internal energy of steam to do work against the piston, which is connected to the flywheel. The mechanical energy of a flywheel can then be transmitted to other parts or systems. Here now is a model of a steam engine. This type of steam engine was invented by James Watt in the late 70s.